All right, welcome back. So we're going to start chapter 3 of AI engineering by Chip Huyen. I actually made a video on it yesterday, but like very quickly got sidetracked and decided to just scrap it and start back over. So this is chapter 3. This is evaluation methodology. The more AI is used, the more opportunity there is for catastrophic failure. We've already seen many failures in the short time that foundation models have been around. A man committed suicide after being encouraged by a chatbot. Lawyers submitted false evidence hallucinated by AI. Air Canada was ordered to pay damages when its chatbot gave a passenger false information. Without a way to quality control AI outputs, the risk of AI might outweigh its benefits for many applications. As teams rush to adopt AI, many quickly realize that the biggest hurdle to bringing AI applications to reality is evaluation. For some applications, figuring out evaluation can take up the majority of the development effort. Due to the importance and complexity of evaluation, this book has two chapters on it. This chapter covers different evaluation methods used to evaluate open-ended models, how these methods work, and their limitations. The next chapter focuses on how to use these methods to select models for your application and build an evaluation pipeline to evaluate your application. While I discuss evaluation in its own chapters, evaluation has to be considered in the context of a whole system, not in isolation. Evaluation aims to mitigate risks and uncover opportunities. To mitigate risks, you first need to identify the places where your system is likely to fail and design your evaluation around them. Often, this may require redesigning your system to enhance visibility into its failures. Without a clear understanding of where your system fails, no amount of evaluation metrics or tools can make the system robust. Before diving into evaluation models, it's important to acknowledge the challenges of evaluating foundation models. Because evaluation is difficult, many people settle for word of mouth. For example, someone says that the model X is good, or eyeballing the results, and the Hugging Face leaderboard might be a version of that. This creates even more risk and slows application iteration. Instead, we need to invest in systematic evaluation to make the results more reliable. Since many foundation models have a language model component, this chapter will provide a quick overview of the metrics used to evaluate language models, including cross, entropy, and perplexity. These metrics are essential for guiding the training and fine-tuning of language models and are frequently used in many evaluation methods. Evaluating foundation models is especially challenging because they are open-ended, and I'll cover best practices for how to tackle these. Using human evaluators remains a necessary option for many applications. However, given how slow and expensive human annotations can be, the goal is to automate the process. This book focuses on automatic evaluation, which includes both exact and subjective evaluation. The rising star of subjective evaluation is AI as a judge, the approach of using AI to evaluate AI responses. It's subjective because the score depends on what model and prompt the AI judge uses. While this approach is gaining rapid traction in the industry, it also invites intense opposition from those who believe that AI isn't trustworthy enough for this important task. I'm especially excited to go deeper into this discussion, and I hope you will be too. Challenges of evaluating foundation models. Evaluating ML models has always been difficult. With the introduction of foundation models, evaluation has become even more so. There are multiple reasons why evaluating foundation models is more challenging than evaluating traditional ML models. First, the more intelligent AI models become, the harder it is to evaluate them. Most people can tell if a first grader's math solution is wrong. Few can do the same for a PhD level math solution. It's easy to tell if a book summary is bad if it's gibberish, a lot harder if the summary is coherent. To validate the quality of a summary, you might need to read the book first. This brings to us a corollary. Evaluation can be so much more time consuming for sophisticated tasks. You can no longer evaluate a response based on how it sounds. You'll also need to fact check, reason, and even incorporate domain expertise. Second, the open-ended nature of foundation models undermines the traditional approach of evaluating a model against ground truths. Without traditional machine learning, most tasks are closed-ended. For example, a classification model can only output among the expected categories. To evaluate a classification model, you can evaluate its outputs against the expected outputs. If the expected output is category X, but the model's output is category Y, the model is wrong. However, for an open-ended task for a given input, there are so many possible correct responses. It's impossible to curate a comprehensive list of correct outputs to compare against. Third, most foundation models are treated as black boxes, either because model providers choose not to expose models' details, or because application developers lack the expertise to understand them. Details such as the model architecture, training data, and the training process can reveal a lot about a model's strengths and weaknesses. Without those details, you can evaluate only a model by observing its outputs. At the same time, publicly available evaluation benchmarks have proven to be inadequate for evaluating foundation models. Ideally, evaluation benchmarks should capture the full range of model capabilities. As AI progresses, benchmarks need to evolve to catch up. A benchmark becomes saturated for a model once the model achieves the perfect score. With foundation models, benchmarks are becoming saturated fast. The benchmark GLUE, General Language Understanding Evaluation, came out in 2018 and became saturated in just a year, necessitating the introduction of SuperGLUE in 2019. Similarly, natural instructions 2021 was replaced by supernatural instructions in just a year later in 2022. MMLU in 2020, a strong benchmark that many early foundation models relied on, was largely replaced by MMLU Pro. So even one of their biggest, baddest, strongest benchmarks only lasted about 4 years. Last but not least, the scope of evaluation has expanded for general purpose models. With task-specific models, evaluation involves measuring a model's performance on its trained task. However, with general purpose models, evaluation is not only about assessing a model's performance on known tasks, but also about discovering new tasks that the model can do, and these might include tasks that extend beyond human capabilities. Evaluation takes on the added responsibility of exploring the potential and limitations of AI. The good news is that the new challenges of evaluation have prompted many new methods and benchmarks. Figure 3-2 shows that the number of published papers on LLM evaluation grew exponentially every month in the first half of 2023 from 2 papers a month to almost 35 papers a month. So these are written specifically about how to evaluate LLMs. Figure 3-1 shows the trend of LLM's evaluation papers over time. So we can see, boom, they're going up through the roof. And it'd be fun if I could see the evaluation of alignment papers and safety papers, because I have a feeling they're going down, which is kind of scary. But it looks like there's a reference here of the author's own analysis, and uh, I don't see where to see more. Oh, okay, so this is where that data was came from. Is this paper here? But yeah, it'd be interesting to see alignment and safety research if that has gone up or gone down or flatlined. But let's keep going. So, in my own analysis of the top 100 AI related repositories on GitHub, as ranked by the number of stars, and I made an accidental highlight there, so let me get rid of that. There we go. I found over 50 repositories dedicated to evaluation as of May 2024. When plotting the number of evaluation repositories by their creation date, the growth curve looks exponential as shown in figure 3-2. So this was 3-1. We've also got, so these are papers, and similar to how the research is increasing, we can see in 3-2. Number of open source evaluation repositories among the 1,000 most popular AI repositories on YouTube is similarly exponentially increasing. So these next few years are all about evaluation. The bad news is that despite the increased interest in evaluation, it lags behind in terms of interest in the rest of the AI engineering pipeline. Oh, interesting. Okay. So even though it's increasing so much, it's late to the game. It's one of the weaker components, which makes sense why it's increasing so much. Balduzzi et al. From DeepMind noted in their paper that developing evaluations has received little systematic attention compared to developing algorithms. According to the paper, experiment results are almost exclusively used to improve algorithms and are rarely used to improve evaluation. Recognizing the lack of investments in evaluation, Anthropic called on policymakers to increase government funding and grants, both for developing new evaluation methodologies and analyzing the robustness of existing evaluations. To further demonstrate how the uh, investment in evaluation lags behind other areas in the AI space, the number of tools for evaluation is small compared to the number of tools for modeling and training and AI orchestration, as shown in figure 3-3. Inadequate investment. So here's figure 3-3. According to the data sourced from my list of the 1,000 most popular AI repositories on GitHub, evaluation lags behind other aspects of AI engineering in terms of open source tools. So here's other aspects. Evals. So while evals is the aspect we're talking about, the other aspects besides that are agent, AI interface, prompt engineering, inference optimization, AI orchestration, and the big one, modeling and training. Evals is the least. Inadequate investment leads to inadequate infrastructure, making it hard for people to carry out systematic evaluations. When asked how they are evaluating their AI applications, many people told me that they just eyeballed the results. Many have a small set of go-to prompts that they used to evaluate models. The process of curating these models is ad hoc, usually based on the curator's personal experience instead of based on the application's needs. You might be able to get away with this ad hoc approach when getting a project off the ground, but it won't be sufficient for application iteration. This book focuses on a systematic approach to evaluation. All right, so next section, understanding language modeling metrics. Foundation models evolved out of language models. Many foundation models still have language models as their main components. For these models, the performance of the language model component tends to be well correlated to the foundation model's performance on downstream applications. Therefore, a rough understanding of language modeling metrics can be quite helpful in understanding downstream performance. As discussed in Chapter 1, Language modeling has been around for decades, popularized by Claude Shannon in his 1951 paper, Prediction and Entropy of Printed English. The metrics used to guide the development of language models haven't changed much since then. Most autoregressive language models are trained using cross entropy or its relative perplexity. When and perplexity is the name of of a company, but it's also the name of a concept in the science of AI. Um, and it's a concept that is similar to the concept of cross entropy. I don't know that much more about it. When reading papers and model reports, you might also come across bits per character, BPC, and bits per byte, uh, BPB, which is that, would that ever not be eight? Oh, okay. Um, so both are variations of cross entropy. All four metrics, cross entropy, perplexity, bits per character, and bits per byte, are I guess it would be the number of bits in the byte that are turned on. So like if you had, yeah, okay, that's probably what that is. Are closely related. If you know the value of one, you can compute the other three, given the necessary information. While I refer to them as language modeling metrics, they can be used for any model that generates sequences of tokens, including non-text tokens. Recall that a language model encodes statistical information, how likely a token is to appear in a given context, about languages. Statistically, given the context, I like drinking blank, the next word is likely, it's more likely to be tea than charcoal. The more statistical information that a model can capture, the better it is at predicting the next token. In machine learning lingo, a language model learns the distribution of its training data. The better this model learns, the better it is at predicting what comes next in the training data, and the lower its training cross entropy. As with any ML model, you care about its performance, not just on the training data, but also on your production data. In general, the closer your data is to a model's training data, the better the data can perform on your data. What? That doesn't make sense. The better the model can perform on your data. Compared to the rest of the book, this section is math heavy. If you find it confusing, feel free to skip the math part and focus on the discussion of how to interpret these metrics. And I urge you, if you're intimidated by the math part, and I would say this is the best time in ever in human history to learn math. Jump on ChatGPT and have it try to break it down and just spend a little bit of time on it. Like I'd say don't feel free to skim through it and kind of not have everything fully grokked, if you're familiar with that term. But in this day and age, with the you know ChatGPT Pro and all these tools, and then forget about ChatGPT, like rewind it back before ChatGPT was released. Khan Academy, Three Blue Brown. Like this is the best time ever in human history to learn math. So I say um, you can skim it, but do not skip it, I would say. Even if you're not training or fine-tuning language models, understanding these metrics can help with evaluating which models to use for your application. These metrics can occasionally be used for certain evaluation and data deduplication techniques, as discussed throughout this book. All right, so now we're going to learn about the mathematical concept of entropy, which is good because I think that's a term a lot of people have heard, but an actual, real, intuitive mathematical understanding of it, I think very few people have. So, um, and I think I wonder if first of all, let me check the okay, it's only at the 19-minute mark, so we'll definitely dive into this. I'll probably have to take a quick break here, but uh, But yeah, so I'm going to take a quick break and then we're going to waste no time on side tangents as I tend to do a lot. And we're just going to read what the book says and try to get through as much of the book as possible here. So I'll take a quick break, come back, and then read about entropy. All right, I'm back. Let's keep going on this. So entropy. Entropy measures how much information on average a token carries. The higher the entropy, the more information each token carries. The more bits are needed to represent a token. Let's use a simple example to illustrate this. Imagine you want to create a language to describe positions within a square, as shown in figure 3-4. If your language has only two tokens, as shown as A in figure 3-4, each token can tell you whether the position is upper or lower. Since there are only two tokens, one bit is sufficient to represent them. The entropy of this language is therefore 1. Okay, so figure 3-4, two languages describe positions within a square. Compared to the language on the left, so uh, uh, the tokens on the right, B, carry more information, but they need more bits to represent them. Okay, so on A, you describe them with top and bottom, but on B, you have to do top, bottom, left, and right. So you can no longer just describe a position on whether it's top or bottom. You have to add another word. You have to say top left or top right, similarly for the bottom. So you need more words to describe the position of the tokens on the right in square B rather than the tokens on the left in square A. If your language has four tokens, shown as B in figure 3-4, each token can give you a more specific position, upper left, upper right, lower left, or lower right. However, since there are now four tokens, you need 2 bits to represent them. The entropy of this language is 2. This language has higher entropy since each token carries more information, but each token requires more bits to represent. Intuitively, entropy measures how difficult it is to predict what comes next in a language. The lower a language's entropy, the less information a token of a language carries. The more, okay, the more predictable that language. In our previous example, the language with only two tokens is easier to predict than the language with four. You have to predict among only two possible tokens compared to four. This is similar to how if you can perfectly predict what I will say next, what I say carries no new information. Cross entropy. When you train a language model on a data set, your goal is to get the model to learn the distribution of this training data. In other words, your goal is to get the model to predict what comes next in the training data. A language model's cross entropy on a data set measures how difficult it is for the language to model for the language model to predict what comes next in this data set. A model's cross entropy on the training data depends on two qualities. Number one, the training data's predictability, measured by the training data's entropy. Number two, how the distribution captured by the language model diverges from the true distribution of the training data. Entropy and cross entropy share the same mathematical notation, H. Let P be the true distribution of the training data and Q be the distribution learned by the language model. Accordingly, the following is true. The training data's entropy is therefore um, uh, P P H of P or P of H. Well, it's function H with yeah. So P is okay. So if entropy and cross entropy have the same uh, mathematical notation H, okay. P is the true distribution of the training data. So so the distribution of the true distribution of the training data um, is that training data given to entropy or cross entropy. So the training data's entropy is the true distribution of the training data, whether or not it's given to entropy or cross entropy. The divergence of Q with respect to P can be measured using the callback Leibler KL divergence, which is mathematically represented as D subscript QL, open paren P, double pipe Q, and these are capital P and capital Q, close paren. So let's get the LLM to uh, uh, say unpack this equation into plain English. Unpack the equation in the screenshot into plain English. All right, and we'll let it sit on that and keep reading as it's going. The model's cross entropy with respect to the training data is therefore that, and I'll get that unpacked as well. I'll say good. Now unpack this equation next, please. All right, keep going as it's going. Cross entropy isn't symmetric. The cross entropy of Q with respect to P, so H P comma Q, is different from the cross entropy of P with respect to Q, H Q comma P, the Q and the P in parentheses. A language model is trained to minimize its cross entropy with respect to the training data. If the language model learns perfectly from its training data, the model's cross entropy will be exactly the same as the entropy of the training data. The KL divergence of Q with respect to P will then be zero. You can think of a model's cross entropy as its approximation of the entropy of its training data. All right, so let's see. Hopefully, this first one. No, okay. Yeah, so Pro isn't the best one to use for something like this. Model, even just the most basic O4 is probably fine. O1 without reasoning would be fine too, but this is the fastest model and it would probably be just fine. But anyway. Next section is bytes per character and bits per byte. One unit of entropy and cross entropy is bits. If the cross entropy of a language model is 6 bits, this language model needs 6 bits to represent each token. Since different models have different tokenization methods, for example, one model uses words as tokens and another uses characters as tokens, the number of bits per token isn't comparable across models. Some use the number of bits per character, BPC, instead. If the number of bits per token is 6, and on average each token consists of 2 characters, the BPC is 3 divided by 2 equals 3. One complication with BPC arises from different character encoding schemes. For example, with ASCII 2, each character is encoded using 7 bits, but with UTF-8, a character can be encoded using anywhere between 8 and 32 bits. A more standardized metric would be uh, uh, would be bits per byte, BPB. The number of bits a language model needs to represent 1 byte of the original training data. If the bits per character is 3, and each character is 7 bytes, or 7/8 of a byte, then the bit per bit, oh, sorry, bit per byte, those two B stand for different things, is 3 divided by 7 divided by 8. So 3 divided by the product, or the result of 7 divided by 8, and that would equal 3.43. Cross entropy tells us how efficient a language model will be at compressing text. If the uh, bit per byte of a language model is 3.43, meaning it can represent each original byte, 8 bits, using 3.43 bits, this language model can compress the original training text to less than half the text's original size. All right, so that sounds like it's very necessary with how much data to process to be able to do it more efficiently through this method of um, tokenization. Sounds like it would go very far. All right, so the next one is perplexity. Perplexity is the exponential of entropy and cross entropy. Perplexity is often shortened to PPL. Given a because that yeah okay Given a data set with the true distribution P, its perplexity is defined as uh, PPL. So the perplexity of P equals 2 raised to the entropy, yeah, P, that. The perplexity of a language model with the learned distribution on its dataset is defined as that. And let's get this unpacked in plain English next. Hopefully, it's finished the first one, so we can have another one going. There, it has finished that one. So now we'll get into this, and we'll say good. Now unpack this next. Okay, so let's read what it says. So the plain English. So okay, so the KL, so in plain English, it asks if the true probabilities are given by P, how inefficient or surprised would I be if instead I used Q to describe those probabilities? That's pretty good. I like that, assuming it's true, but it's a good way to. So yeah, that's what this means. Is if the true probabilities are given by P, how inefficient or surprised would I be if instead I used Q to describe these probabilities? So like, is Q a good enough, yeah, so like the divergence of Q with respect to P. So like if, yeah, so how much would the answer change if I used Q instead of P? All right, and then the next one, oh, it's still thinking about that, so I'll keep going. So, okay, so there we go. The perplexity of a language model with the learned distribution Q on this dataset is defined as perplexity of P comma Q equals 2 raised to the H of P comma Q. If cross entropy measures how difficult it is for a model to predict the next token, perplexity measures the amount of uncertainty it has when predicting the next token. Higher uncertainty means there are more possible options for the next token. Consider a language model trained to encode the 4 position tokens, as in figure 3-4b, perfectly. The cross entropy of this language model is 2 bits. If this language model tries to predict a position in the square, it has to choose among 2 equals 4 possible options. Thus, this language model has a perplexity of 4. So far, I've been using bit as the unit for entropy and cross entropy. Each bit can represent 2 unique values. hence the base of 2 in the preceding perplexity equation. Popular ML frameworks, including TensorFlow and PyTorch, use NAT, natural log, as the unit for entropy and cross entropy. NAT uses a base of E, the base of natural logarithm. If you use NAT as the unit, perplexity is the exponential of E. So perplexity of Q, P comma Q equals E, which is something like 2.1. What is E? Let's look it up. Okay, that took me to women's jumpsuits on eBay, um, which is obviously what I was looking for. So let's see here. Uh, mathematical E. Okay, yeah. So well, it's closer to 3. It's 2.71, but if I remember correctly, it's like pi, where it's an irrational number. So um, yeah, yeah, and E matters a lot because it's the square root of uh oh, because it's uh why does E matter? Yeah, so it's irrational like pi. It's also transcendental, meaning that it is not a root of any non-zero polynomial with rational coefficients. Uh, is pi transcendental? Let's have a quick discussion about this with the AI. Okay, so briefly tell me the mathematical number E. That's like super important, right?
Absolutely. The mathematical constant E is approximately 2.71828. It's the base of natural logarithms and is crucial in calculus, particularly in growth processes and compound interest. Its properties make it fundamental in both pure and applied mathematics.
Why can't you just use pi instead?
Great question. Pi is essential in geometry, particularly with circles, but E is fundamental in growth and decay problems. E is the base of natural logarithms and is used in calculus for functions involving rates of change. Each constant has its own unique role in mathematics.
Is pi a transcendental number like E is?
Yes, both pi and E are transcendental numbers. This means they aren't roots of any non-zero polynomial equation with rational coefficients. Essentially, they can't be expressed as the solution to any simple algebraic equation, highlighting their complexity and uniqueness in mathematics.
All right, that's all I need to know. All right, moving on. Let's see here. Let's see here. So far I've been using the where am I? Um, people. Let me just start at the top of this page. So far I've been using bit as the unit for entropy and cross entropy. Each bit can represent two unique values, hence the base of 2 in the preceding perplexity equation. Popular ML frameworks, including TensorFlow and PyTorch, use NAT, natural log, as the unit for entropy and cross entropy. NAT uses the base of E and the base of natural logarithm. If you use NAT as the unit, perplexity is the exponential of E. Due to the confusion around bit and nat, many people report perplexity instead of cross entropy when reporting their language model's performance. All right, and here's the unpacked plain English. So this next one would be, oh, here, yeah, so hit the third one now. So the next one would be your total average encoding cost equals the best possible encoding cost, um, plus whatever extra burden you incur by using Q. Okay. All right, moving on. So perplexity, interpretation, and use cases. As discussed, cross entropy, perplexity, bit per character and bit per byte are variations of language models' predictive accuracy measurements. The more accurately a model can predict a text, the lower these metrics are. In this book, I'll use perplexity as the default language modeling metric. Remember that the more uncertainty the model has in predicting what comes next in a given dataset, the higher the perplexity. What's considered a good value for perplexity depends on the data itself and how exactly perplexity is computed, such as how many previous tokens a model has access to. Here are some great general rules. More structured data gives lower expected perplexity. Um, okay. More structured data is more predictable. For example, HTML code is more predictable than everyday text. Um, if you see an opening HTML tag like head, the HTML tag head, you can predict that there should be a closing tag, which in HTML would be the left pointed chevron, then a forward slash, then a HEAD, and then a right pointed chevron nearby. Therefore, the expected perplexity of a model on HTML code should be lower than the expected perplexity of a model on everyday text. The bigger the vocabulary, the higher the perplexity. Intuitively, the more possible tokens there are, the harder it is for the model to predict the next token. For example, a model's perplexity on a children's book will likely be lower than the same model's perplexity on War and Peace. For the same dataset, say in English, character-based perplexity predicting the next character will be lower than word-based perplexity, predicting the next word, because the number of possible characters is smaller than the number of possible words. The longer the context length, the lower the perplexity. The more context a model has, the less uncertainty it will have in predicting the next token. In 1951, Claude Shannon evaluated his model's cross entropy by using it to predict the next token conditioned on up to 10 previous tokens. As of this writing, a model's perplexity can typically be computed and conditioned on between 500 and 10,000 previous tokens, and possibly more, upper bounded by the model's maximum context length. For reference, it's not uncommon to see perplexity values as low as 3 or even lower. If all tokens in a hypothetical language have an equal chance of happening, a perplexity of 3 means that this model has a 1 in 3 chance of predicting the next token correctly. Given that a model's vocabulary is in the order of 10 thousands and 100 thousands, these odds are incredible. Other than guiding the training of language models, perplexity is useful in many parts of an AI engineering workflow. First, perplexity is a good proxy for a model's capabilities. If a model is bad at predicting the next token, its performance on downstream tasks will also likely be bad. OpenAI's GPT-2 report shows that larger models, which are also more powerful models, consistently give lower perplexity on a range of datasets, as shown in Table 3-1. Sadly, following the trend of companies being increasingly more secretive about their models, many have stopped reporting their models' perplexity. So this is Table 3-1. Larger GPT-2 models consistently give lower perplexity on different datasets. So source comes from 2018. So the larger the GPT-2 model, the lower complexity on the data set. So here's the size, and here's the complexity. So, yep. Warning, complexity might not be a great proxy to evaluate models that have been post-trained using techniques like supervised fine-tuning and reinforcement learning from human feedback. Post-training is about teaching models how to complete tasks. As a model gets better at completing tasks, it might get worse at predicting the next tokens. A language model's perplexity typically increases after post-training. Some people say that post-training collapses entropy. Similarly, quantization, a technique that reduces a model's numerical precision and with it its memory footprint, can also change a model's perplexity in unexpected ways. Recall that the perplexity of a model with respect to a text measures how difficult it is for this model to predict this text. For a given model, perplexity is the lowest for texts that the model has seen and memorized during training. Therefore, perplexity can be used to detect whether a text was in a model's training data. This is useful for detecting data contamination. If a model's perplexity on a benchmark's data is low, this benchmark was likely included in the model's training data, making the model's performance on this benchmark less trustworthy. This can also be used for deduplication of training data. For example, add new data to the existing training dataset only if the perplexity of the new data is high. Perplexity is the highest for unpredictable texts, such as texts expressing unusual ideas, like my dog teaches quantum physics in his free time, or gibberish, like home cat go I. Therefore, perplexity can be used to detect abnormal texts. Perplexity and its related metrics help us understand the performance of the underlying language model, which is a proxy for understanding the model's performance on downstream tasks. The rest of the chapter discusses how to measure a model's performance on downstream tasks directly. All right, so this is how to use a language model to compute a text's perplexity. A model's perplexity with respect to a text measures how difficult it is for the model to predict that text. Given a language model X and a sequence of tokens, X's perplexity for this sequence is shown in that equation, where uh, that part of the equation, the first part to the left-hand side without the raised to the negative 1 over n, denotes the probability that X assigns to the token X subscript I, given the previous tokens X1 in a series up to X uh, subscript I minus 1. To compute perplexity, you need to access the probabilities or log probs the language model assigns to each next token. Unfortunately, not all commercial models expose their model's log probs as discussed in chapter 2. Okay. I was thinking that would be a fun operator thing to try to use that equation to well, you know what? It still might be. So let's give it let's do a little bit of a side tangent here and see if this makes any sense at all to operator. So and then I'm not sure if I can do a screenshot in operator. Oh, you know what? I can save it. So let's do a we're gonna let's save this under downloads. All right, and then go to downloads, and then upload that screenshot, and then we're gonna say evaluate Yeah, there we go. There we go. There we go. There we go. Use that equation to compute the perplexity. Use that equation to compute the perplexity in the text at this link. So let's have it. Let's do like a Shakespeare play. All right, so let's go with comedy of errors. That sounds like a right one to use. So we get the complete text. There we go. Um, and we'll say, show your work, think out loud. Work, think out loud. Go step by step. Prove and verify. All right. So there we go. We see operator opened up its own browser. It uses Bing. Unfortunately, it can't access certain sites like YouTube yet. I was hoping, basically, the minute it can do it, I'm going to have it analyze the transcripts of my whole YouTube channel. That's kind of like the point of having this YouTube channel. Kind of early on was I want to have a data store of myself online. The problem is, since I use YouTube, it doesn't belong to me. So that's kind of the goal of that Sovereign Cloud series. Look at this. This is cool. It's gonna use a calculator. It looks like it's found a perplexity calculator on Hugging Space. It found that link, gave it the right link. So there we go. Now it's copying only the text of the play and not the anything else. Now it's putting it into the perplexity calculator. So that isn't that cool that it knows how to do that? I wouldn't even think to use a calculator like that. So there we go. It copied the portion of the comedy of errors and prepared it for perplexity calculation using the Hugging Face tool. Should I proceed? Yes, proceed. All right, so it's going to give me back the perplexity using a calculator on Hugging Face. Look at that. Isn't that cool? And I didn't tell it to use a calculator. It just came up with that on its own. It looked up which calculators to use. And but we do have an error here. I don't know what's going on. Well, anyway, while that's going, let me move the bookmark forward. All right, there's a lot to get through. This is a major section, so let me check the clock next. Clock is almost at that hour mark. So, okay, so it looks like there wasn't enough space to put in there. So yeah, proceed. So it's just going to do it in short sections at a time, not for the whole text. Oh, still got an error. So for some reason, I'm not able to get to use this calculator here. But isn't that cool? I mean, you can see the world we're heading into when all this stuff does work. It was just released for the first time like yesterday or the day before, and it's still very much in beta. So, this is the world we're entering. But that's going to be it for this video. This is just a kind of a clean place to stop right at this exact evaluation section. And I'm already near that hour mark, which is typically all I'm good for without an extended 10-15 minute break. So yep, that's it for this video. Thanks for watching and see you in the next one.